Hello everyone, welcome back to week 9 of Event-Driven Computing. Hopefully you've all had a chance to recuperate a little bit over the mid-semester break, and if needed, catch up on a few bits and pieces. I've certainly been busy preparing various different bits and pieces, marking and looking at the exam for the course, so there'll be a bit more information on that coming later on. Let's take a quick look at what else is happening in Event-Driven Computing at the moment. Programming Assignment 2 is due on Friday. That's our PetriNet assignment, and of course there'll be one more Programming Assignment 3. That's going to be available this week. It's going to be a little smaller in scope than Programming Assignment 2, but 20% of the course grade as usual. And we also have workshops this week, so if you have questions about Programming Assignment 2, feel free to please do come along to workshops and ask them. If you are struggling on anything, please don't hesitate to get in touch, ask about extensions, those sorts of things. I am, as you're probably aware, generally quite happy to work with you on extensions if need be, but you do need to ask. So that's what's going on there. I did want to do a little quick recap because I'm seeing a few common questions coming up about PetriNets on the discussion boards. So let's just have a quick start. A little bit of a recap of some of the things we can do with PetriNets. Hopefully, if you're really stuck, this will help you out a little bit. But I also encourage you to go back and review our PetriNet lecture, because we do spend some time going through the basic PetriNet structures that you'll need in this assignment during that lecture. I think it's in the end portion of the lecture that we go through that. We are going to take a little bit of time to recap the fundamentals of functional reactive programming. We've had a couple questions come up in terms of how that relates with the observer patterns, so we're going to try and address those. And then we're going to take a look at the material from this week, which is the functional reactive programming primitives. Now, for those of you who haven't already done so, please make sure that you have access to the reference book that we're using in this course for functional reactive programming, and that's this one just here, Blackheath and Jones, Functional Reactive Programming. It gives a well, it's the best overview that I've found so far, and I've looked at a whole lot of different materials on the topic, so hopefully you find it as useful and as practical as I think it is, and as I've found it to be. But if you don't have access to this book, make sure you create an account on Manning. You should have full access to the text for free. This is not through the course readings section of the site at the moment, because the publisher is not connected to our library, but you can still access the full material for free, so please make sure that you do that. So without further ado, let's take a quick recap of some bits and pieces with PetriNets and try to address some of the common problems that we might be seeing. So to start off with, let's remind ourselves of the fundamentals that we're dealing with when we have to work with PetriNets. They work a little bit differently than our regular FSAs, so it's always helpful to remind ourselves of the constraints that we are working under with PetriNets. So first up, we want to remember that there's no magic happening in here. Everything in a PetriNet happens as a result of some sort of a transition. So in order to move from one place to another, a transition has to be triggered. Transitions are enabled and disabled if their input conditions are met or not met, respectively. So again, to recap, if I have a place and a transition and another place, this transition can only fire if this place's input condition is fulfilled. So that's better. There we go. So this transition is only enabled if this input condition is fulfilled, and therefore you cannot action this transition unless the input condition is fulfilled. So right now, you cannot fire this transition because its input condition is not fulfilled, but as soon as I fill the input condition, this transition becomes enabled and I can fire it, like so. Similarly, if I have multiple input conditions, like so, all of the input conditions must be met. So I cannot fire this transition until both input conditions are met. At the point both conditions are met, the transition can be fired, the inputs are consumed, and then an output is produced, like so. So we went, in this case, from 2 down to 1. That's a really important concept. So in terms of we're trying to simulate a railway network, the first things first is how do we get, depending on how we're representing things, how do we get a train into a particular section of track? We cannot simply have, if this place represents one section of track and this place here represents another section of track, this by itself doesn't do anything because you have to somehow get a token into this place in order to enable this transition to occur. You might be tempted to make this an initial state, but that implies that there is already a train in this section of track to begin with. That's not going to work, and it also means that there's only ever one train, the one that's there at the start, and as soon as it's gone, we can't add any more. So how do we create a structure that allows us to get trains into the network and flowing through the network? And one of the ways that we can approach this is looking at some of the design patterns that were introduced to us in section 6.2 of the notes. So I highly encourage you to go back and take a look at section 6.2 of the notes. In this case, we have the producer and consumer structures. So in this case, we have a single producer or a place that is initialized with token present in it, like so. And you can see that the input condition for the transition is that this place is populated, but it's also one of the output conditions. So every time this transition fires, it's going to consume this input, and then it's going to produce the outputs like so. And now both places are populated, and we can keep repeating this, and what that'll result in is this input gets consumed again, and then the output gets produced, and we end up with 2 tokens here and 3 tokens here. Now we probably don't want to have multiple tokens in this other place here, especially if the tokens were to represent the presence of a train in a section of track, because, well, a train in a section of track, we said that we don't want to have multiple trains in the same section of track because then things go crash. We want to avoid that. So there are some other mechanisms that we can put in place to help with that. And one such example of one of those mechanisms is the buffer mechanism. So I encourage you to take a look at the buffer mechanism. So there's the producer. The consumer we can use at the other end of things. It's one that takes tokens out of the network, so when a train exits the network we can use a consumer pattern, and when we combine them together we end up with this kind of a pattern here with a buffer. So that's initialized, those are initialized. So if we want to add a train into the network, well, we need both of these conditions to be satisfied, and at that point we effectively get this. Now, because this input condition is no longer satisfied, we can't keep pushing more in here. But once this condition is satisfied again, say the train exits the network, and we end up back here, and now another train can move through, and we can chain them together into a more complex structure like this. So hopefully most of you have already picked up on this basic structure and how we can extend on it. We can also do a couple other interesting things with these. I mean, there's not really any limit to the interesting things that we can do, but we can apply the same basic concepts and we can say, okay, well, let's say that we have a transition, this transition here, that we only want to be able to fire when there happens to be some other condition that is met. Let's say this transition should only be enabled when there is a train in some other section of track. Let's say that this over here represents that other section of track. And we'll just add arrows in here that represent a train coming in and a train leaving at some point. What we can do is we can add an input condition from there down here, like so. So now this transition is only enabled when this place is also populated with a token. Now, because we don't necessarily want to remove the token from here, we just want it as a check, we can loop it back like this. Looks very similar to our producer. The only difference is that there are times when the token can be added or removed from this section. And we have effectively added a check that says this transition is only enabled when this place has a token in it. Whether that represents a train or the absence of a train is another question. But so that's a data structure that we can consider. And there's a bunch of other ones that we can apply to help us go through the logic of these tracks, and I encourage you to come along to workshops this week if you are still unsure about how you could apply this. One thing that I really want to stress is you need to try to step through your networks to make sure that they actually work. Don't just draw something that you think works and then only to come back and it doesn't actually apply. If you're coding your implementation faithfully to the PetriNet that's provided, your implementation isn't going to work if your PetriNet doesn't work. So I encourage you to carefully set up each section of the PetriNet and step through it with tokens on paper like we're doing here to make sure that it works the way that you expect it to. All right. That's that. Let's take a quick revisit of functional reactive programming. So just before the mid-semester break, we started looking at functional reactive programming. We looked at the fundamentals of this concept. We had already talked about the idea of the observer pattern, and we had this observer pattern, which was a way of dynamically registering and receiving and handling events, reacting to events, and then dynamically unregistering. And we talked about, okay, well, this is the way that most modern event-driven frameworks work, especially because typically they're built on top of APIs and you need to connect your code base into the code base of the API in order to have it functional, or to have it work rather. So we then introduced this idea of functional reactive programming as an alternative to the observer pattern. We identified a few different issues with the observer pattern, namely issues with registration, issues with handling state, and issues with order, among other things. So we introduced this new concept, functional reactive programming, which is more declarative, where as part of the programming you're explicitly linking these things together and declaring upfront how you want everything to work. And we introduced that through the Sodium FRP API for Java. And then we started to take a look at some of the basics, and we played around with a basic cell, and we looked at how we can set this up so that as you modify the value of one variable, or one variable is changed in response to an event, that the change to that variable propagates its changes across to a variety of other parts of the system automatically for us, much in the same way that we can do with the observer pattern, but in a much more declarative manner. And we also started to talk about the concept of event streams, the idea that in addition to having these variables or cells that we want to have a value that dynamically changes, just the same way as if you have a mathematical function and you change the inputs to that function, the outputs would automatically change. In theory, we had this with the cells, but we also talked about the idea that events themselves are typically discrete. So as you receive a sequence of events, what if we treat the events not as discrete and separate things, but rather as a stream of events upon which we can perform generalized actions such as transformations, merging of streams, mapping, filtering of events, and those sorts of things. And that's what we're going to be looking at a bit more this week, and that's hopefully what you've been reading a bit more about thus far. One of the questions that came up this week was noting that a lot of functional reactive programming frameworks are implemented using the observer pattern, and yet it is professed in the reference material that we've been looking at that functional reactive programming fixes a lot of problems with the observer pattern. So the question that we got was, well, how are they actually different from each other if it just uses one to implement the other? And specifically, the question was asking, okay, well, the observer pattern has an issue with order, or at least the book tells us that the observer pattern has potentially an issue with order, and how is it that functional reactive programming fixes this? And the answer to that question is that functional reactive programming requires us to declare the order up front. So one of the issues with the observer pattern is that in general, the design pattern for the observer pattern itself doesn't specify how we implement the management of the collection of listeners, and that's one of the problems. There are a lot of assumptions that we make about how listeners are managed in the observer pattern. There's this idea that it might be done with a list, for instance, and you add in one observer, and then you add another observer, and another observer, and another observer, and you add all these observers in, and there's this assumption that we make that when an event occurs, it's going to then enact these observers in order. So if an event comes in, it's going to start by calling this observer, then calling this observer, then calling this observer, and calling this observer in order. But it's never actually specified how we manage this. The idea is that they just all get called, but the sequencing is never properly specified in the pattern. And so if you implemented this with something like, for instance, a hash set rather than a list of some sort, then by using a hash set, these could get registered into the list like 1, 2, 3, 4, and then they get called that way, which is in a different order than you might expect. We also have issues in terms of, okay, well, what happens if we remove this listener and then later re-add it? Does it get added at the end, or does it get re-added into its previous place? What if we have optimizations in place to improve performance that result in these being automatically reordered? Do we implement this using a set or a list? There are a bunch of different questions and assumptions that we can make about how to use the observer pattern and how it works. With functional reactive programming, while some implementations may follow a rough observer pattern in their implementation, the goal is that everything is explicitly mapped out in order. So if you have each of these is considered like one discrete time unit, and if you want something to happen after so an event comes in, it enacts on various different event streams. So you might have several different streams that are all based on the same source, but event comes in, it enacts all of these different streams, and then if you wanted to perform different actions or transformations on each of these streams, that would then happen in a subsequent that would potentially happen subsequently, so you would have your transformations applied on top of all of these, and that is all considered to be occurring in the same time step. So the language of the functional reactive programming paradigm is based on the idea that if you have multiple events occurring at the same time, or if you have the same event propagated to multiple streams simultaneously, that all of this is happening simultaneously and there is no dependency on the order in which these are done. And to achieve this, we specifically have the cell or subject, depending on which framework you're using, but we specifically have these two data types. We have the stream and the cell, and the stream represents the sequence of events coming into the system, and the cell represents a piece of data that can change, and we use specific interactions between them, which I'll come back to in a little bit, in order to facilitate this idea that if things are happening simultaneously, they are treated as simultaneous, and they are declaratively programmed as simultaneous. Whereas if one event, if something should happen one after another in a specific order, the transformations and different actions, whatever we want to apply, those are explicitly declared in the order that they should occur, and they are then applied in the order that they should occur. So rather than being multiple listeners that get executed in sequence, so again, if I draw a new version of this, so if we had in a traditional observer pattern, you might have an event comes in, you'd have a list of things, a list of observers, and depending on the way that the list is set up, assuming it was in order, you would action it, this one, then this one, then this one, then this one. If these applied 4 different transformations on the event, or performed 4 specific actions that should occur in order, then that relies on the observer pattern actually properly handling them in order. In functional reactive programming, rather, each stream, the event is propagated into the stream, an action occurs of some sort, and then the next action, they're all explicitly declared to occur in order. So the stream is only acting upon, or the observer pattern is only really acting upon this first one, and then when that one explicitly completes, then that one declares that this one follows it. So the order is baked into the way that you declare and write your code. I know this is all getting quite abstract, so feel free to please ask questions on Piazza or in workshops this week if you're confused about this. It's quite different from the way that many of us are used to programming. Okay, so with some of that in mind, let's take a look at some of the key primitives. So in functional reactive programming, there are several key operations or primitive operations that we can perform on either cells or subjects, depending on your framework, and streams of events, or observable streams, again, depending on your framework. So we're using the Sodium framework in the reference material, but this conceptually applies across pretty much all functional reactive programming implementations, even if they all do implement things slightly differently. So with that in mind, let's start by taking a look at one of these primitives, and we're going to start with the map primitive. And we've already talked a little bit about this at week 8's lecture, but let's revisit it to begin with. So you'll see in the book that there are 2 different types of diagrams used to visually represent what is going on in functional reactive programming. You have one flowchart style diagram that represents how everything looks, and that's going to look a little bit something like this. Get to the right section. That's going to look something a little bit like this. So what we have here is we have a source of events and a stream of events, and then an operation of some sort. And this is the map operation. It shows us that we have the event and we transform it into what is a string. That might be a little bit hard to see. Let me just zoom in a little bit. There we go. That should be a little bit better. So we have the event that comes in as a unit or nothing value, as they've stated, and it gets converted into an empty string. This is the operation. So you would write in here something that demonstrates what the before looks like and what the after looks like for every value. It's a succinct representation of what this particular map is going to do, and that gets generated into an output stream, and that gets output into a cell like this called text. So that's the basic setup of that type of diagram. The other type of diagram that we have is called a marble diagram. The marble diagram represents how things occur over time, especially if you have lots of different ways that variables or values can be handled. So in this case, we would say, here's our input stream. Still a little bit. So here's our input stream, here's our output stream, here's our map operation, we would draw this something like this, and this would be, again, a description of what the operation actually does, usually in some sort of visual representation. And in each of these circles, we might also put in a value. So in this case, it would be a U up here and an empty stream down here. And that would be a representation of our map event. This type of diagram is good for representing more complex operations, especially if there are a variety of different discrete values and outcomes that you can get from those discrete values. So marble diagram representation versus flowchart representation. I'm not going to expect you to be able to draw these necessarily, but I do expect you to be able to read these. And if you want to see some more examples of marble diagrams, because I know they don't get used very much in these chapters of this book, you can find in the appendix at the back here. Well, I mean, there's lots of good stuff in the appendix. First of all, you have a full API. So if you are having trouble finding the API for Sodium, take a look back in the appendix. And here's a reference comparison between different functional reactive systems. And I think it's the very last appendix here. You can see a bunch of marble diagrams that represent how things are handled. So this is an example of a marble diagram for a merge stream here. So you can have stream 1, stream 2, and then the resulting stream. And it demonstrates what the operation should be for that. We can also see this representation here for a snapshot operation. Here's one for a filter operation. So if you're stuck, take a look at those for reference. I will generally provide marble diagrams in the same format as they are in the book if I am going to put them anywhere for you. So that's a simple map. What does the map do? The map basically transforms a stream of events from one type to another, and if you have multiple events in your stream, which might look something like this, each event gets transformed in the same way according to what's in here. You can potentially omit this as well and just have the diagram, as we saw just a moment ago, just have the diagram written like this, where you have the value. So if we had a map operation that added 1 to everything, for instance, 1, 2, if we had the values 1 and 2, the map operation would look like 2 and 3 just here. And that's what our map operation would look like in the sense of a marble diagram or a timeline diagram. So that's that. Let's take a look at some code examples of how this works. I know that some of the examples in the reference material are maybe a little bit convoluted if you are just getting started. So I've come up with a few basic examples that might help out with this. So here is my example of map. And what we have here is we have, well, firstly, we have this code here which sets up the window. So this is a GUI based piece of code, or a graphical user interface piece of code. So we have this that sets up the window. This puts things onto the window and gets everything ready to go. And this is where all the magic is happening just here. Let's take a look at what this does. So I can type into the text box and it's going to output onto the label, which is just to the right of the text box. And as I type in, it's going to reflect the output or it's going to reflect the value of each input event on the stream, and it's going to reflect that onto the output label. Now, this particular map function, what it's going to do is it is going to, anytime I type in a curse word, or in this case explicitly curse word, it's going to bleep out that section. And you can see I can keep typing in, and as soon as I untype that, we get back there. Let's take a look at the code in a bit more detail. So we have our input, which is the text input, that can output an event stream, which is why it's called suser changes here, like so. So that's going to output a stream, which is this one just here. And what we're going to do is we're going to take that stream and we're going to pass it through a map function. Let's not do that. We're going to pass it through a map function. And the map function looks like this. This is the map function just here. It takes one input, which we're calling t in this case, and t is the value of the piece of text currently held in the text box. Every time I type into the text box, that's going to trigger a new event, and the complete text of the text box is getting sent as an event on the event stream. And then what we're going to do is anytime curse word, the actual text curse word appears, but you can think of a few probable actual curse words that we could swap in there. Anytime that appears, it gets converted into a bunch of stars. And then we are going to plug that into a cell just to hold the value, because we need to use a cell to display it on the label, because the label takes a cell as an input. So we have this label here, takes a cell as an input, that's this cell just here. So what we've done is we have taken a stream of events, we've declared that every event as it comes through we're going to apply this mapping to, which basically wipes out any curse word that we see and replaces it with stars, and then pushes that to a label, or pushes that to a cell which is reflected in a label. So that's our map example. Let's take a look at a slightly different pattern. We can take a look at the filter primitive. Now, the filter primitive is going to so if I have a sequence of inputs like so, the filter primitive accepts some inputs and not others. Like so. Looks something like this. So as opposed to the map function, where every input event in the event stream was mapped across to an event on the output stream, the filter takes a Boolean function, that is a function that returns a true or false value, and if the function returns true, then the event is propagated from the input stream to the output stream. If the Boolean function returns false, then the event does not get propagated across from the input stream to the output stream. Let's take a look at what that looks like in code. So here's my filter example just here. Just need to recompile that. Okay, here's our filter example just here. Again, we have another input box, and what this filter example does is if someone, if an input contains the curse word, in this case again just the text curse word, then it's not going to propagate that to the output. So let's take a look and see what the difference here is. So if I type in the same stuff as usual, as soon as I type in the D in curse word, you'll see that it's stopped me outputting anything. This string contains curse word. So anytime I add an event, or anytime I type into this string, the event that gets propagated contains curse word, and as a result that is filtered out. As soon as I remove one of the characters from here, you can see that the full output is then propagated out again. So the filter removes events that meet a specific criteria. So this is just a Boolean function. In this case, t.contains returns true or false. True if it contains it, false if it doesn't. Now we want all cases where it does not contain it, so we've just put the not operator in front. If t does not contain curse word, then we allow it to continue through. If it does, then it gets left out. And once again, that gets propagated onto the text input. All right, let's take a look at another of the primitives with another piece of example code. I'm going to move over to the snapshot primitive. So the role of the snapshot primitive is to pull in values from cells. You might be wondering, why can't I just use global variables and pull those in? If you want to maintain state between events in an event stream, you may have noted that the book says, no, you really don't want to do that. You shouldn't use global variables to maintain state between invocations of our different functions. So if we're using a map, for instance, we want to explicitly avoid any cases where we are pulling in other sources of information from outside of the function itself. We don't want to maintain state between the functions. It's functional. We don't want to maintain state between invocations of functions. So what do we do instead when we actually do want to maintain state? Well, we use the cells. The cells exist for a reason, and the specific reason that the cells exist is so that we can bring in this additional state information in a way that does not break the ordering of things. If we just bring in variables in the way that we might normally do so when coding, then when we get simultaneous events, we run into weird race conditions. We want to explicitly avoid race conditions, and it's not even that we run into race conditions, because the programming language itself can deal with that for us, but it brings us back to the problem of, okay, stuff happening out of order. And to get around that, we explicitly use the snapshot primitive. And the snapshot primitive says that if we have a stream of events like so, and we have a cell like so, and the cell holds a specific value at different points in time, let's say the value here is 1 and the value here is 2, the value changes at this point in time here. What the snapshot does is every time an event propagates, we combine it with the value in the cell in some manner, and then we can propagate that value, an updated value out. And we can potentially also update our cells as part of this if we really want to. Something like this. So let's take a look at the example code for that. So here we've added in a second text input, and that text input contains the value A. Now we are explicitly going to treat this input as a cell as opposed to a stream of events, because we're not interested in what the user types into this field. We're only interested in it when the user interacts with the other input fields. So you'll see input 2, which has the value A in it to begin with, input 1 does not, or input 1 is blank to start with. Again, gonna compile. Okay. Right, Alright, so here's input 2 over on the left, input 1 on the right, and I can type anything I like in there, and its value just is getting stored in a cell and reflected into a cell. And it's only when events come in from me typing into the other box on the right that that's going to result in this snapshot function being called. And the snapshot function, what does it do? Well, it takes T1. T1 is the it takes T1 and T2. T1 is input 1, the function that this is being called on. T2 is input 2, the first parameter of this. You can supply multiple sets of parameters, so we could have an input 3 and an input 4. In this case, there would be a input 3 here and a T3 and so on and so forth. Input 2 is the cell that we are interested in. Input 1 is the source of events as an event stream. So what happens is every time an event comes in on this event stream specifically, then we run this function that does something with the event that has just occurred and the current value of the cell, which is T2 here. In this case, it is going to combine them together with a space, and it's going to spit the answer back out. And that is what's going to get shown in the text output. So it was A originally, let's just go back to that, and then as I type in here, you can see anything I type in here followed by a space and then the value of this. If I change this to something else and make this G, and as I type in there, you can see it's using the current value of the cell. The reason why we use snapshot and cells is because of that race condition issue that we talked about earlier, in order to preserve order when multiple events propagate simultaneously, or theoretically simultaneously, within the same transaction time slot in this functional reactive programming framework. When that happens, we want to make sure that the cell's value is viewed consistently. So the snapshot operation looks at the value of the cell at the very start of the transaction, and if there are multiple things happening simultaneously, all of them will lock down the value of that cell right at the very start, and the cell's value will not get updated or changed until the end of that transaction, which could include multiple different things happening simultaneously. So this is what allows us to deal with the ordering of operations issue that we were worrying about before, and this is why we even bothered to use them in the first place rather than using something like global variables. So that's our basic snapshot example, and the last one we want to look at is merge. The merge operation is quite simple. It takes some number of input streams and it produces an output stream that is the combination of the two. Now, there's a few different ways that this works in various different reactive programming frameworks or functional reactive programming frameworks. The way it works in Sodium is fairly simple. If we have one input here, and one input here, and then two at the same time just here, this one comes directly down here, this one is copied directly down here, and these two are combined together in some way based on an arbitrary function, much like the map that we were looking at before, where you got to supply an arbitrary function to specify how things are transformed. In the merge, when events come through discretely on multiple different streams, then they are just added or combined into the same output stream. So you can have multiple input streams mapping to one output stream. Why might we want multiple input streams mapping to one output stream? Well, maybe we have a bunch of different buttons on the user interface and they all do something similar, or we want to perform the same actions on this set of different buttons. you can have each button's inputs mapped to a single stream, and therefore every time a button gets pressed, it creates an event on that stream. And then we can merge all of those streams together to create one stream of all of the different button presses combined together, if we wanted to. This one is interesting, and there are a few different ways that this can be implemented. So the default merge operation is this one here, where you get to define it, but there is also an or else operation where it just ignores this one altogether, and you just get this first one, and they don't get combined. And different reactive programming frameworks have a variety of different operations for handling the different merge cases, but Sodium FRP has the two. It has merge and it has or else, and the or else is just take the first one. Let's take a look at some example of the code for that merge. So here's our merge example just here. We are going to compile it. And run it. Bring it on over. Okay, let's quickly talk about what this is doing first up. So we have two text inputs this time. They're the ones that are going to get merged together. And what we have is we have our arbitrary merge function. So in this case, anytime I type into either of these text inputs, the output is going to get propagated to the output stream. So if I type an A in here, A gets propagated to the output stream. If I type a B in, B is the thing that's getting propagated. And I can type in a bunch of different stuff. Remember that each of these text boxes, every time I type in them, the entire string is getting sent out as the event, which is just the way that these text inputs are set up to work. But as you can see, I type in this one, it switches over to this one. So anytime an event is occurring on either of these boxes, that is what's getting sent out. Now, you might be wondering, Ian, how can I actually type in two boxes simultaneously? How can multiple events happen at the same time? And that's a good question. We have an example for that as well to help get a sense of how this is all working. So let's do that. Compile that and run it. Okay, now this one only has one text box, and what I've done is I've applied a map and a merge together. It looks something like this. Where's my mouse go? Here it is. So what I've done is something like this. So I have one input stream like so, and an output stream, and I've got a map operation that links these two together, and then I have a third output stream that is taking the combination of this one, and putting them together. So it's one event that gets propagated to multiple streams, and then those two streams are then combined with a merge operation. That's what we're looking at there. So let's take a look at the code. The code looks something like this. So in this case, I have the map operation. What does the map operation do? Well, it replaces all of the vowels in the text with stars. That's what we're doing. And then the merge is going to merge the source and also this stream. It's going to perform the same action that we were looking at previously, which is combine the two of them together. The same behavior as we saw in the snapshot example and also in the merge example just before. It's just set up this time they are actually running simultaneously. So let's take a look at that. So as I type in, for example, hello, so the first stream contains hello, just as normal. The mapped output contains H star LL star, and if I type that in a bit slower, you'll see HELLO, like that. And the merged output is the output of the first stream space, the output of the second stream, and that's what's getting displayed on the screen here, like so. So these are actually being considered or handled by the framework as simultaneous. I'm taking two streams, I'm operating on them, I'm combining them together. And that's our example of merge. A lot of the times the events that we're working with will do things like will not be simultaneous. In fact, most of the time they won't be simultaneous. But what this approach to programming allows us to do, it allows us to perform various transformations on our inputs in a clear and declarative way. And we have the option of having all of these different transformations and then tapping them as separate streams and doing things with the outputs of those streams, representing data on screen in different forms if we want to, all happening simultaneously. And before, the way that we would have to do this was a bit more clunky. We would have to declare observers and then link observers to observers and all of those sorts of things. With functional reactive programming, we declare the behavior, we declare the way that we want our data to flow through the system, and then the output then represents all those operations on it. So hopefully this has been useful to get us started, and hopefully this will make Programming Assignment 3, or hopefully this will start to make sense as we work through Programming Assignment 3, which will be available later this week. And that is all for this week's pre-recorded session. I look forward to seeing you all in person next week, or at least, live next week. Feel free to ask any questions on Piazza as usual. Hopefully we'll see you in workshops, and have a good time. We'll catch you in the next one.